Today we're looking at key characteristics of polynomial functions and how to use this sheet to graph the function and then look at all of its key characteristics. And we're actually going to start with the characteristics and then we'll do some graphing. So we know that the lead coefficient here is x cubed. The lead term is x cubed. The coefficient here would be a 1. And the degree here is 3. So that means that the parent function that we're looking at here is just simply y equals x cubed. Or f of x equals x cubed. So this is a cubic function. It's because the lead coefficient is 1, which is positive 1, the end behavior for our odd degree with a positive lead coefficient, our end behavior is going to be in quadrants 1 and 3. And so when we think about that, when we really talk about end behavior, what we're trying to do is we're trying to match up the sign on the infinity term. So basically, x is going to positive infinity this way, right? These end arrows mean this, positive infinity here. So if you're in quadrant 1, you've got x is going to positive infinity and y is going to positive infinity. So our end behavior would basically be the interval that includes this positive and positive infinity for x and y. Whereas in quadrant 3, we know that we're going towards negative infinity for y and negative infinity for x. And so we could describe our end behavior using this interval notation, meaning this is where we're headed towards. There's some more specific language around end behavior, but for us, for now, we're just going to focus on the quadrants and the signs in those quadrants and then apply them to infinity. Okay, now we get into the zeros. Well, the thing is, we could figure out the zeros if we could factor this, and this does look factorable. So let's go ahead and factor that. Let's do it up here in this little space. And so we've got x cubed plus 6x squared plus 8x. And we can factor out the GCF, which is x, leaving us with x squared plus 6x plus 8. Two numbers that multiply to 8 but add to 6 would be 2 and 4. And so we know that if we factor this to x plus 2 and x plus 4, that's going to be our fully factored version of this function. So this is going to equal 0 if x equals 0, or if x equals negative 2, or if x equals negative 4. So our zeros, and I'm just going to actually write this function in here, the factored form of it, so that later you remember why we did this. And when you set that to 0, that will be true if any of these factors is 0. So that's going to be when x equals 0, or negative 2, or negative 4. Those are our zeros. That means we're going to have points here, right? And at negative 2, and at negative 4. So this is our negative 2, and this is our negative 4. And that, of course, is 0. I'm going to go ahead and, since I'm starting to graph, I'll go ahead and number my number line. I'll make it true to scale, not jump numbers. Okay, 1, 2, and 3. This will be negative 1, negative 3. Okay, then our range. Why don't we do domain and range once we finish factoring? But I can tell you for any polynomial function, the domain is going to be all real numbers. That's always true for all polynomials. Decreasing intervals, increasing intervals, and turning points. Well, we're actually going to use a little technology here to find our turning points for our graph. So I've got Desmos here ready to go. I've put in my factored form. I can see my function here. And I'm just going to touch the function and it's going to show me those 2 points, right? Negative 3.155 and 3.079. That's one of my turning points. And the other one, the other one is at negative 0.845 and negative 3.0. 0.79. You know what? We can round this. Let me go ahead and model that for you. We're going to just go ahead and round this to tenths, because that's probably the most accurate that we can draw. Okay, so here are our values: negative 3.2, that rounds to 2, and positive 3.1, and negative 0.8, and positive, I'm sorry, also negative 3.079. So those are our turning points. Remember, our turning points define where the graph turns from being increasing to where it's decreasing and then increasing again. And so those turning points change that direction. So the increasing intervals, and if we look at this, right, it's increasing all the way up to this x value. So when we talk about the interval where it's increasing, we want to talk about it in terms of x. So we would say from when x is greater than negative infinity, which is this end behavior here, all the way up to that point, but not including the point. And then it increases again from this point to positive infinity. And so we look at our x value there, boop, boop, our x value there, at negative 0.8 greater than x greater than positive infinity. And remember, no greater than or equal, only greater thans, okay? Only betweens. So we put our minimum value and our maximum value for the first increasing part, and then our minimum and maximum for the next increasing part. So our decreasing interval is between here, from when x is negative 3.2 to when it's negative 0.8. And there's only one, right? So the minimum at negative 3.2 and the maximum at negative 0.8. Okay, so we are ready to sketch this graph. We're going to plot these turning points at negative 3.2 and positive 3.1, so right around there. And then at negative 0.8 and negative 3.1 there. Okay, so we'll sketch our graph coming through here. Try to make that a curve, not a point, when you go through those turning points. So you want to come in a little before the point. So that you can curve in and out of that. Don't forget your little arrow tips showing that it's going to positive infinity, negative infinity, quadrant 1 and quadrant 3. Our range here, it looks like, because it's going from positive infinity to negative infinity, that's all real numbers. Just like our x values are going from positive infinity to negative infinity, or negative to positive, however you want to think about it. It's using all the numbers on the number line. Same is true for the range. And so the range is also all real numbers. And you could actually write that with interval notation, saying it's going from negative infinity to positive infinity, negative infinity to positive infinity. Okay, so this is basically everything we're trying to figure out. Turning points, where is it increasing, where is it decreasing? And quite frankly, I think it actually really helps sometimes. I like to kind of color code this a little bit with a highlighter. So if I were doing my increasing points, I'd be saying it's from here to here, and then again from here to here. And then it's decreasing from here to here. So for all of these values of x, right? Negative 3.2 to negative 0.8, which my highlighting's not perfect, but when we talk about increasing and decreasing intervals, we're really talking about where on the x-axis is that making a change. So that's why we're always seeing x in here on our intervals. Okay, just a little reminder about some of those fun facts. Okay, that's it.